Welcome to the Spring Boot Advanced interview series on microservices and transactions. Over the next 30 questions, we'll move from fundamentals to distributed transactions, each with a clear answer, a code snippet, a memorable real-world example, and, where useful, a flow diagram. Let's dive in. Here's our roadmap. We start with microservices fundamentals, move into resilience and communication patterns, then cover transaction core concepts, and finish with the hardest topic, distributed transactions. 30 questions in total. Section 1. Microservices Fundamentals. What is microservices architecture, and how does Spring Boot enable it? Let's start with the foundation. Microservices architecture means we take one large application and break it into small, focused services, each owning a single business capability and its own database. Spring Boot makes this practical, with auto-configuration, an embedded server, and starter dependencies, so each service boots in seconds. Spring Cloud then layers on discovery, configuration, gateways, and resilience. Picture Amazon. Cart, payment, shipping, and reviews are all separate services. If reviews go down, you can still check out. That isolation is the whole point. Monolith versus microservices. When would you choose each? A classic question. Monolith or microservices? A monolith is simple. One deploy, easy local development, strong transactional consistency, but it scales as a single block, and one bad release can take everything down. Microservices give you independent scaling, independent deployments, technology freedom, and fault isolation, but you pay for it with network latency, distributed data, and serious operational overhead. My honest advice: start with a well-structured monolith and split into services only when team size or scaling pain becomes real. Netflix didn't start with microservices, they evolved into them. How do microservices communicate? Synchronous versus asynchronous? Services talk to each other in two main styles. Synchronous communication, REST or gRPC, means the caller waits for a response. It's simple and intuitive, but it creates tight coupling and cascading failures. Asynchronous communication uses message brokers like Kafka or RabbitMQ. Services emit events and move on, giving you decoupling and resilience at the cost of eventual consistency. Use synchronous when you need an immediate answer, like a balance check. Use asynchronous for state changes and fan-out. Think of a restaurant. Paying the bill is synchronous. You wait. Telling the kitchen to start cooking is asynchronous. What is service discovery and how does Eureka solve it? In the cloud, service instances come and go, and their IP addresses change constantly. Hard-coding addresses is a recipe for outages. Service discovery solves this. Eureka acts as a registry. Every service registers itself on startup and can look up others by logical name. Clients cache that registry locally and resolve names to live instances. Kubernetes and Consul offer similar capabilities. The analogy I love: it's like the Contacts app on your phone. You call mom, not her phone number. Even if she changes her SIM card, the name still works. What does an API gateway do? Why Spring Cloud Gateway? An API gateway is the single front door to your system. Instead of clients knowing about dozens of services, they hit one endpoint, and the gateway handles routing, authentication, rate limiting, cores, and logging in one consistent place. Spring Cloud Gateway is reactive and non-blocking, built around a clean predicate and filter model. The big win is that cross-cutting concerns live at the edge, instead of being copy-pasted into every service. Think of a hotel front desk. Guests never wander into the kitchen or boiler room. One reception routes every request to the right department. What is client-side load balancing in Spring Cloud? Client-side load balancing flips the traditional model. Instead of routing every request through a central load balancer, the client itself fetches the list of healthy instances from discovery and picks one often round robin. Spring Cloud Load Balancer does this, and you enable it with a load-balanced REST client, web client, or FAN client using LB-style URIs. The benefit is one fewer network hop and lower latency. It's like walking into a supermarket and choosing the shortest checkout line yourself, instead of waiting for a manager to assign you one. How does centralized configuration, Spring Cloud Config, work? Configuration sprawl is a real problem when you have dozens of services across multiple environments. Spring Cloud Config centralizes it. A config server, usually backed by Git, stores all configuration, and each service pulls its settings at startup based on its name and active profile. You get one source of truth, full version history, and the ability to change configuration without redeploying code. With refresh scope and the actuator refresh endpoint, you can even update values live. Think of it as a single company policy handbook. Update it once and every office follows the new rule. How do you trace a request across many microservices? When a single user request fans out across 10 services, debugging "why is this slow" becomes impossible without distributed tracing. The idea is simple. A unique traceit is generated at the edge and propagated through every hop. Micrometer tracing, the successor to Sleuth, handles that propagation automatically, and you export the spans to a tool like Zipkin or Jaeger to visualize the full timeline. You can then correlate every log line by traceit. It's exactly like a parcel tracking number. One ID shows every warehouse and truck your package passed through, and precisely where it got stuck. Section 2. Resilience in Communication. What is a circuit breaker, and how does Resilience 4J implement it? A circuit breaker protects your system from cascading failures. If a downstream service starts failing, you don't want every caller piling on and making it worse. Resilience 4J implements this with 3 states: closed, where calls flow normally; open, where it fails fast without even trying; and half open, where it sends a few probe requests to check recovery. It's lightweight and annotation-driven, and you pair it with a fallback method for graceful degradation. The perfect analogy is an electrical fuse. When the current spikes, the fuse trips to protect the whole house instead of letting the wiring burn. Explain retry, timeout, and bulkhead patterns. Beyond circuit breakers, 3 patterns work together. Retry reattempts transient failures, but always with exponential backoff and jitter, never a tight loop that hammers a struggling service. Timeout ensures you never wait forever. Every external call gets a hard cap. Bulkhead isolates resources, so one slow dependency can't consume every thread in your pool and starve everything else. Layer these with a circuit breaker, and you get true resilience. The name bulkhead comes from ships. Watertight compartments mean that if one floods, the rest keep the vessel afloat. How do you implement rate limiting in microservices? Rate limiting protects your services from overload, whether from a traffic spike or an abusive client. You can enforce it at the edge with Spring Cloud Gateway's request rate limiter, typically backed by a Redis token bucket so the limit is shared across gateway instances. You can also apply per-service limits with Resilience 4J's rate limiter. When a client exceeds the limit, return an HTTP 429 with a retry after header, so well-behaved clients back off. Think of a nightclub with a one-in one-out policy at capacity. It keeps the people already inside safe from a dangerous crush. What is idempotency, and why is it critical in microservices? Idempotency means that performing the same operation multiple times has the same effect as doing it once. In distributed systems, this is non-negotiable. Because retries, and at least once message delivery guarantee, you'll see duplicate requests. The standard solution is an idempotency key supplied by the client, plus a store of already processed keys. If you see a key again, you return the original result instead of reprocessing. This is absolutely critical for anything involving money. Think of an elevator button. Pressing it 5 times doesn't summon 5 elevators. A payment retried twice must still charge the customer exactly once. When and how do you use async messaging? Kafka/RabbitMQ. Asynchronous messaging decouples the producer of an event from its consumers, which buys you buffering, independent scaling, and resilience. Kafka is a high-throughput, ordered, replayable log, ideal for event streaming and rebuilding state. RabbitMQ is a flexible traditional message broker with rich routing. Either way, you unlock event-driven choreography and eventual consistency between services. Picture a restaurant's ticket rail. Waiters pin up orders, cooks pull them when they're ready, and neither stands around waiting for the other. The queue absorbs the dinner rush. How do you secure microservices with OAuth 2 and JWT? Securing microservices statelessly is best done with OAuth 2 and JWT. A central authorization server authenticates the user and issues a signed JWT access token. The gateway validates that token, and downstream services simply trust the signature and read the claims. No shared session store required, so you scale horizontally with ease. Scopes and roles inside the token drive fine-grained authorization. The analogy: a festival wristband. Security checks your ID once at the entrance and gives you a wristband. After that, every food stall just glances at the band. Nobody re-verifies your passport. Section 3. Transactions Core. What is @transactional and how does Spring implement it? The @transactional annotation is how Spring gives you ACID guarantees on a single database. Under the hood, it uses an AOP proxy. When you call the method, the proxy begins a transaction, lets your code run, commits if it returns normally, and rolls back if a runtime exception escapes. So in a place order method, if saving the order succeeds but deducting inventory throws, the order save is rolled back too, all or nothing. It's exactly like a bank transfer. The debit and the credit must both succeed or both fail. You never want money to leave one account and vanish before reaching the other. Explain transaction propagation. What does requires_new do? Propagation controls how a transactional method behaves relative to an existing transaction. The default, required, joins the caller's transaction or starts one if none exists. Requires_new is the interesting one. It suspends the current transaction and runs in a completely independent transaction that commits on its own. The classic use case is audit logging. Imagine a money transfer fails and rolls back, but you still need a permanent record that the attempt was made. By writing that audit entry in a requires_new transaction, it survives even when the outer transaction is rolled back. What are isolation levels, and which problems do they solve? Isolation levels define how much one transaction is shielded from concurrent ones, trading consistency against performance. Read uncommitted allows dirty reads and is rarely used. Read committed prevents dirty reads and is the common default. Repeatable read guarantees that rows you've read won't change if you read them again. Serializable is full isolation. It even prevents phantom rows, but it's the most expensive. Picture two agents trying to book the last concert seat at the same instant. Stronger isolation stops both from seeing it as available and double selling it. What are the default rollback rules? Checked versus unchecked exceptions? This is one of the most common Spring gotchas in interviews and in production. By default, Spring rolls back only on unchecked exceptions, runtime exceptions, and errors. Checked exceptions do not trigger a rollback unless you say so. People get burned by this. A checked payment declined exception is thrown, but the half-completed order quietly commits because nobody configured rollback for. The fix is to be explicit. Use rollback for to specify which exceptions should roll back, and no rollback for the ones that shouldn't. Never assume. Always declare your intent. Why does that transactional fail on self-invocation? Internal calls. Here's a subtle senior-level trap. At transactional is implemented with a proxy that wraps your bean. The transactional behavior only kicks in when a call comes from outside the bean and passes through that proxy. If a method calls another method on the same object using this, the call goes directly to the target and completely bypasses the proxy, so the inner method's transaction annotation is silently ignored. The fixes are to move the inner method to a separate bean, or to self-inject the proxy. The same limitation affects at async and at cacheable. It's like an internal memo that skips the mailroom. It never gets the official transaction stamp. What is a read-only transaction and why use it? Marking a transaction read-only is a small change with real benefits. When you set read-only equals true, Hibernate knows nothing will be modified, so it skips dirty checking and the flush at the end, which speeds up read-heavy methods. Many databases and drivers can also route read-only transactions to replicas or take lighter locks. As a best practice, annotate your query and read service methods this way. It's like opening a document in view-only mode. The application knows you won't edit, so it skips all the autosave bookkeeping and feels noticeably snappier. Optimistic versus pessimistic locking. When to use each? Concurrency control comes in two flavors. Optimistic locking adds a version column. Everyone reads freely, and the conflict is only detected at commit time when versions don't match. Then you retry. Pessimistic locking takes the lock up front with a select for update, blocking others until you're done. Choose optimistic when conflicts are rare and concurrency is high. That's your sensible default. Choose pessimistic for hot contended rows, where retries would be expensive, like the last item in inventory. Wikipedia is optimistic, edit freely, and only clash if someone saved first. A bank vault is pessimistic, one person at a time. Why don't local at transactional transactions work across microservices? This is the pivotal question that bridges into distributed transactions. A local at transactional only governs the database of the service it runs in. Each microservice owns its own database, with its own transaction boundary, and there's no shared connection that can commit or roll back across them. Worse, once you make a network call to charge a payment, that side effect has already happened. A local rollback can't reach across the wire to undo it. It's like an email. You can't unsend it after you hit send. That's why we need patterns like Saga and the outbox pattern, which we'll cover next. Section 4. Distributed transactions. Two-phase commit, 2PC versus Saga. Which and why? When a business operation spans multiple services, you have two main strategies. Two-phase commit uses a coordinator that asks every participant to prepare, locks them, and then tells them all to commit together. It's strongly consistent, but it's blocking and fragile. If the coordinator or one participant stalls, everyone is stuck holding locks, which doesn't scale in the cloud. The Saga pattern instead chains a series of local transactions, each with a compensating action to undo it on failure, accepting eventual consistency. Microservices overwhelmingly favor Sagas. Think of 2PC as everyone freezing until all signed together, versus a Saga as a relay race where each runner completes their leg. Saga. Choreography versus orchestration. Trade-offs? Sagas come in two coordination styles. In choreography, there's no central brain. Each service listens for events and reacts by emitting its own. It's beautifully decoupled, but the overall business flow becomes implicit and hard to follow when something goes wrong. In orchestration, a central orchestrator explicitly commands each step and tracks the Saga's state. That gives you a clear, observable flow and easy error handling, at the cost of a component that can become a bottleneck or single point of focus. Choreography is a dinner party where guests self-organize from social cues. Orchestration is a wedding planner directing each vendor step by step. What is the transactional outbox pattern, and what does it solve? The outbox pattern solves the dual write problem. If you save an order to your database and then publish an event to Kafka as two separate steps, a crash in between leaves them inconsistent. The order exists, but nobody was notified, or vice versa. The fix is elegant. Within the same local transaction that saves the order, you also insert the event into an outbox table. Since it's one atomic commit, they can never disagree. A separate relay process, often using change data capture, reads the outbox and publishes to the broker, guaranteeing at least once delivery. It's like dropping a letter in your own outbox tray. The instant it's written, it's safely queued for the mail carrier. What is eventual consistency, and how do you design for it? Eventual consistency means that after a change, the different services will agree, but not instantly. There's a short propagation window. This is a deliberate trade from the CAP theorem. You give up immediate strong consistency to gain availability and scale. Designing for it means embracing idempotent event handlers, retries, compensating actions, and clear service-level expectations about how quickly things reconcile. Crucially, be honest with users about pending states. You've seen this yourself. When you transfer money, the app shows pending for a moment. The balances reconcile shortly after, not in the very same millisecond, and that's perfectly fine. What is CQRS, and when is it worth the complexity? CQRS, Command Query Responsibility Segregation, separates your write model from your read model. Commands that change state go through a normalized, validation-heavy write model, while queries are served from denormalized projections optimized for exactly how the UI needs the data. This lets you scale reads and writes independently and tailor multiple read shapes. But it adds real complexity, and usually eventual consistency between the two sides, so reach for it only when read and write requirements genuinely diverge. Think of a newspaper. Journalists write in a complex editorial system, while millions of readers hit a fast, cached, read-optimized website. What is event sourcing? How does it differ from CRUD? Event sourcing changes what you store. Instead of saving only the current state and overwriting it, you store the full, immutable sequence of events that led to it. The current state is derived by replaying those events. The payoffs are significant. A complete audit history for free, the ability to time travel and debug exactly how you reached a state, and the freedom to build brand new read projections by replaying history. The costs are real too. Event schema versioning, replay performance, and a steeper learning curve. The perfect mental model is a bank passbook. It lists every deposit and withdrawal, not just today's balance, so you can reconstruct any past balance on demand. How do compensating transactions work in a failed saga? In a saga, once a remote step has committed, you can't roll it back the way a database does. The side effect already happened. Instead, you run a compensating transaction that semantically undoes it. A refund for a charge, a release for a reservation, a cancellation for a booking. When a step fails, you execute the compensations for all prior steps in reverse order. Critically, compensations must be idempotent and retry safe, because they themselves can fail and be retried. Picture an airline booking that fails at seat selection. The system doesn't erase history, it issues a refund and releases the held seat, a business-level undo. How do you implement distributed locking, e.g. Redis/Redison? Sometimes you need to ensure only one instance across your whole cluster touches a resource at a time. That's distributed locking. A common approach is Redison's rlock, backed by Redis. You acquire the lock with a time to live, so that if a holder crashes, the lock auto-expires, and you avoid a permanent deadlock. Always set a lease time, and release the lock in a finally block. For correctness-critical scenarios, look into redlock and fencing tokens to guard against edge cases. The analogy: a cafe with a single bathroom key. Only the person holding the key can enter, and the key has a time limit so nobody hogs it forever if they forget to bring it back. And that wraps up all 30 questions. You're now ready to speak confidently about Spring Boot microservices and transactions. That's all 30 questions. You've covered fundamentals, resilience, transaction core concepts, and distributed transactions. Review the examples, practice explaining each out loud, and you'll walk into that interview with confidence. Good luck.